PCMBI or whatever.
Can we reconvene and take our chairs for the next session?
Yeah.
So what do you talk about?
Things like Snowball Earth.
Oh, there you go. That's still near and dear to my heart.
Yeah, that's why I have to find some things like that. Faint early sun, Snowball Earth.
Yeah, it's great stuff.
I'm not a geologist, so I don't want to do, all of the
That didn't work.
ages,
Did you and Ted
since
over
I
at
don't know
Michigan?
them myself.
Yeah.
We did. And then
Did you want to?
Yeah, I know. Well, I know that we know each other pretty personally.
I need a gavel.
Yeah. Well, you're sort of
I
working
need a
together.
chairman's gavel.
But it
Stand
came
up.
more the other way around. It's
Yell
we
and
met
scream
more
and
as
say, okay,
friends
we're
first
starting.
a
Everybody
long
sit
time.
down.
Oh, okay. Yeah.
Come on, Doug, it's all you.
And Ted
Doug?
and me and Doug.
We need or dim the lights
Ross and
which makes a significant fraction of all.
Just shout.
That's what they always did.
Shout up, tell people to take seats.
That worked. All right.
To competing high schools.
So thank you. So we're going to reconvene for the second session on the natural science of geoengineering. And just as a reminder, we didn't talk about this very much in the opening session, but the ideas that you will hear, probably the idea that you hear the most about is stratospheric aerosols, which we have some understanding of from the natural volcanic analog. Marine cloud brightening, so adding salt aerosols to low marine clouds to increase their albedo. Those are probably the most frequently talked about options for geoengineering, for solar geoengineering. There are certainly other ideas that are on the table. So for example, cirrus clouds warm the planet. So if there are ways of thinning cirrus cloud cover, that would provide a small amount of cooling. And I am sure, and I think Scott mentioned this in the previous session, that as the research progresses, there will probably be other ideas that are developed and that come out. In principle, you could also do something in space, but that's generally believed to be prohibitively expensive. So I'm going to keep my remarks very, very brief. We have a very august panel here. So geoengineering, solar geoengineering is a potential complement to doing mitigation and carbon dioxide removal, as Kate pointed out this morning, as an additional element in a portfolio of managing climate risks. And I think it's very important anytime one thinks about the scientific uncertainties and the risks associated with doing this, is simply to keep that counterfactual in the back of one's mind in thinking about research, in thinking about risks. That we may wind up finding ourselves reaching 1.5 degrees within the next couple of decades. We've probably already come very close to exhausting the carbon budget for 1.5 degree target. So that's the context in which everybody is talking about solar geoengineering. So the purpose of this panel, primarily, what do we know about geoengineering from a combination of climate modeling and natural analogs? What are the uncertainties? So what do we need to know in order to get to a point where we could make some informed decisions about this, assuming that that's something we want to do? And how do we do that? What are the research that needs to be done to get there? So my introduction to this field was a meeting at NASA Ames in 2006. I think most of the panel was at that meeting. This is I don't need to say very much because the panel members here have all been thinking about this problem for at least that long and generally involved in atmospheric science research for much, much longer than that. So on the far end, Alan Robach is a distinguished professor in environmental sciences at Rutgers University. Joyce Penner, Ralph Cicerone, distinguished university professor of atmospheric science at University of Michigan. David Keith, actually the person that originally introduced me into geoengineering. Gordon Mackay, professor of applied physics in the School of Engineering and Applied Science at Harvard, and also professor of public policy in the Harvard Kennedy School. Tom Ackerman, whose name did not make it into the program, is the director for the Joint Institute for the Study of the Atmosphere and Oceans and professor of atmospheric science at the University of Washington. And then sitting next to me is Dan Schrag, who reminded me that he's a professor of geology, as well as a professor of environmental science and engineering at Harvard University, and also the director of the Harvard University Center for the Environment and the director of Science, Technology, and Public Policy program at the Harvard Kennedy School. So I will, so everybody will have roughly 5 minutes for opening remarks. I will give you a 1 minute notice, and I'll set the timer so you'll hear a barking dog at 5 minutes. That was Rebecca, my wife's suggestion last night. And we'll try to leave most of the time for the panel for questions from the audience. So as people are talking, be prepared to come up with the questions that you'd like to ask people. So I will, without ado, pass it to Alan.
Thanks, Doug. Thanks for inviting me here. I'd like to start off with an advertisement. If you haven't had enough geoengineering meetings already, David and Doug and I have organized the first Gordon Research Conference on climate engineering, which will be held this summer in Sunday River, Maine. And it's time now to submit your applications, and we welcome you to come for a whole week talking about climate engineering. We have funding for students and early career people and for some other people too. So we hope you'll consider joining us there. Next. Now, a little history. You might think that this topic has only been studied since 2006 when Paul Crutzen wrote his famous paper, but David's been working on this longer than that, and so has Harry Wexler. I don't know how many of you are familiar with this paper in Science from 60 years ago. Yep. The title was Modifying Weather on a Large Scale, Current Proposals are either impractical or likely produce cures that are worse than the ailment. And he said, when serious proposals for large-scale weather modification are advanced, as they inevitably will be, the full resources of general circulation knowledge and computational meteorology must be brought to bear in predicting the results so as to avoid the unhappy situation of the cure being worse than the ailment. So Harry was a chief scientist for the Weather Bureau, very, very prescient. So we've been doing that. Next slide, please. So at this meeting that, that messed up my, no, I'm just saying your software has changed the size of the font so you can't read it, unfortunately.
Just go without. Just go without, Alan.
So
I can read it.
At this meeting in 2006, I was amazed that people thought how great an idea this was, and I wrote down 20 reasons why it might not be such a good idea. And now I have 27 reasons why it might not be such a good idea, and a few were benefits of outdoor research. And the number one benefit is that if you could do it, you could reduce global warming and all its impacts, and that might be enough for us to live with all the negative aspects. And so, but how can we test these different things? And so with modeling, as Harry Wexler mentioned, this GeoMIP, this Geoengineering Modeling and Comparison Project, we can answer the things that are named, that are in red here. And the next one, next slide. So with using volcanic eruptions as an analog, we can answer some of these things also. So I don't have time to go through all of these. They're in my papers. And then the next slide, but there are some things that can't be answered either with climate modeling or with looking at volcanic eruptions as an analog. And this includes governance, ethics, aesthetics. And so these are the things which are much harder to do. How can we, on the right we have unexpected consequences. On the left we have unexpected benefits. So how can we evaluate those? On the right, we have the moral hazard. If we did it, people would stop doing mitigation. On the left, we have, if people find out about this, there will be more of a push to do mitigation. So these sort of balance each other, but how do we evaluate those? And then there's the issues of military control of the technology, a giant multinational corporation being in charge, the idea that we'll continue to do it forever, even if it's not a good idea. We have examples of military budgets in this country as an example of that, so building things that even the military doesn't want. So Some of these things are much harder to wrestle with. How do we set the planetary thermostat? How do we agree on that? For you young people, this is how we used to set thermostats. How do we agree on that? And at the Asilomar meeting that Doug mentioned, Rob Sokolow went around asking people, what would be the worst consequence of geoengineering? He did a poll, and at the end of the week, he came up with a presentation. The answer was global nuclear war. So it's extreme, but there would be conflict because people couldn't agree. And so how we deal with these issues is much harder, I think, than whether we do small-scale research outdoors or research indoors. And these are things which are issues we really have to deal with. So let me just show the last slide. Harry Wexler also said in 1962, I hope that before we get into large experimentation, that not only will the state of meteorological knowledge be advanced, more advanced than it is now, but also the state of our socio-political affairs as well. These are the issues we're dealing with here. Ah.
That was well done. Within a second.
Okay.
Joyce?
So I would like to, rather than emphasize some of the social issues that I think Alan talked about, talk about what actual things that are possible might or might not work and why they might or might not work. So we, I think, have good knowledge that if we put particles in the atmosphere, in particular in the stratosphere, we will cool the climate. Maybe there will be precipitation changes that we don't understand, but we will cool the climate. But I'd like to emphasize that even with the best instrumented volcanic eruption, which was Pinatubo in 1991, there are disputes about what actual temperature changes came from that natural experiment. So there are estimates in the literature that it was somewhere between as small as 0.14 degrees centigrade and as large as 0.4. So we have that uncertainty. But more than that, I think the issues of how efficient a particular strategy might be are of importance. And the largest one in my mind is the question of if you inject SO2, that has to then convert into sulfuric acid, which then eventually forms particles. And when you form those particles, how large are those particles? If they get too large, then there's not as much reflection of solar radiation, whereas if they stay in just the right range, they might work quite effectively. So we're talking, I think, about field experiments in this panel, and I think to actually find out the answer to this question, not just relying on global models, which after all have very huge grid resolutions, so they don't really resolve the microphysics that we need to know. We need to conduct a fairly large experiment. And in my paper, I think I talked about something that is about 1/10 of the size of the Pinatubo eruption. That's pulled out of the air, right? It's between 0 and 1. And but I think it has to be a fairly large magnitude to really answer this question of microphysics and whether or not the removal from the stratosphere that is thought to be of order 2 years is actually done correctly in these global models. Then there are other issues that are important. We know adding particles to the stratosphere results in a change in stratospheric ozone. How big will that be, since stratospheric ozone acts to heat the stratosphere that causes changes in circulation? How will those things respond, especially at the larger injections that are sometimes talked about? And then the final issue that I put down for stratospheric injection is as these particles descend into the troposphere, they have the opportunity to change cirrus clouds. So if you're adding more cirrus clouds, you're actually heating, whereas if you're decreasing cirrus clouds, you can cool. And we don't know the answer to that. And let me go to the last slide because I have only 1 minute, and that is marine cloud brightening. There are, I think, many issues around this technique. And those issues are things that we could solve with field experiments, I think, although they may have to get, again, very large. But every cloud is seemingly different, and what forces it to form or dissipate is different. And that means we have to go into different kinds of clouds and understand how susceptible they might be to adding sea salt particles. And there are experiments that have been done. The E-piece was mentioned, and it it showed that some clouds brightened and some clouds dimmed. So I think that is definite evidence that we need to know more about this issue. I also mentioned the fact that we've done, and I've done in particular, comparisons of how general circulation models respond to particles compared to how a cloud resolving model at 50-meter horizontal resolution would respond. And the answer is they can respond differently. So the cloud resolving model can heat while the global model cools. And so I think there are questions about how parameterizations are done in these large scale models that make them not correctly predict what's going on in a more highly resolved model. And then the last question is about cloud fraction, which I think there's still a lot of open questions about that whole response. So I have a summary, but and mainly the point, since I'm out of time, is that I think doing these sets of experiments can lead to a slippery slope. Larger experiments are needed, and so to get into this whole experimental regime, I think a governance agreement of some sort is needed. Thanks.
Thanks. David?
So the title of this session was What We Know and What We Ought to Know. But I want to start out with some things that we think we know, or many people think we know in this community or the literature, that I think probably just aren't so. So one of them is there's widely made claim that somehow this solar geoengineering could work for temperature but not for precipitation. So literature is filled with claims that it disrupts precipitation in some way very different from what it does to temperature. Or that it doesn't help ocean acidification. It's another very common claim. Or that it works for the rich but somehow doesn't help or is systematically less effective for the poor. I'm pretty sure that all those three claims as stated are just not supported by the literature or just plain false. That's not to say it works magically, but those claims, as I said them, I think are really not true. And part of it is just getting serious about what we actually know. So I'll just talk about the first and last of those. We've just completed or in the middle of some really interesting research using one of the best models that does tropical cyclones or hurricanes, the GFDL, very high resolution model, working a bit with Kerry Emanuel. And what we discovered kind of in accord with Kerry's thinking is that even partial solar geoengineering, where it just is used to reduce some of the warming, has a very strong effect in dampening the strength of tropical cyclones, which are one of the most damaging effects of climate change, especially to the most vulnerable. And that's a clear example where, if anything, it sort of works better for the precip-side and extreme storms than it does for temperature. Precipitation over land, part of the misconception has been simply due to poor treatment of statistical confidence in models. So if you ask if you do solar geoengineering to, say, cut the rate of warming in half, what fraction of the world's land surface has precip that is driven further, is driven towards pre-industrial versus further away? That is made sort of better or worse if you think pre-industrial is the right answer. And if you throw away the points that aren't statistically significant, it's a very small number of points, if any, depending on the model, where you've actually made it worse. And that really, part of that depends on the statistical significance claim. We've been looking a little carefully now at including with some epidemiological models, at how extreme temperatures hurt people and how that is connected with their income. And it's pretty clear that the poor are harmed the most, and that by reductions, the poor would have the most relative benefit. I also want to talk about field experiments. So we're inching towards a field experiment. We've been doing that for a couple years now, published an early version of what we call the Stratospheric Controlled Perturbation Experiment, and we're now beginning to move towards actually doing this thing over the next few years. I'll say a few words about it. The goal is to make quantitative measurements of some of the aerosol microphysics and atmospheric chemistry that you need to estimate more about the risks and benefits of solar geoengineering in a large-scale model. People often ask, why not just model it? But of course, models are completely dependent on a bunch of parameters which we've got from decades or centuries of observing the world. You don't just make these things in a vacuum. So what we would do is use a balloon with a gondola in the middle stratosphere. The balloon would move at a few meters a second, and the propeller wake turns out to be crucial to this. It makes a well-mixed plume of air that would be a few kilometers long and 100 meters in diameter, into which we can use as a kind of a vessel that we can make quantitative controlled measurements in the stratosphere. We'll start by just injecting ice crystals is the thinking. And the idea is in that well-mixed wake, we can actually measure some of the key parameters to do with the particle-particle interactions that determine the kind of things Joyce was talking about and their interactions with atmospheric chemistry. At least in our current thinking, the balloon operation will be provided by Worldview in Tucson, Arizona, so that's where we'll fly out of. I can say a few words about how it will be governed. I think the first is to say that we, those of us doing the experiment, and it's really me and Professor Frank Koich are the experimental leads, we completely agree that governance of solar geoengineering in general and of experiments is inadequate and contested. And our view is that an experiment like this can actually help to grow governance in a kind of bootstrap way. We think there are three core kinds of governance we need. One is kind of hard governance of environmental health and safety risks, which has to be by an external agency. And there are a variety of external agencies that can do that. In practice, the amount of material we're talking about releasing, which should actually be probably less than a kilogram, is not big enough to, for example, trigger a EIA under the National Environmental Protection Act. But we're going to look to see if we can get what's called a FONSI, a finding of no significant impact under that act. There are also separate checks and balances at Harvard and Worldview. But quite separate from that kind of the physical risks, we completely acknowledge that there are risks to do with just talking about or making solar geoengineering more prominent. The risk that it will embolden the fossil fuel industry to fight harder against emissions controls. And so a core will be to build a scientific, an advisory committee, not just scientific, an advisory committee that is strong and independent and contains a really diverse set of views, including views that are very critical of proceeding down this road, as a way to kind of co-develop structures for governance. And part of the mandate of that advisory committee would be to recommend explicitly how governance might be improved. And I would say that to be clear, we are not unalterably committed to doing the experiment. We're heading down the road of doing that, and depending on what the advisory committee says, depending on what we learn technically, we are certainly willing to stop, because our long-term goal is to build a sustainable effort in solar geoengineering research that allows us to tell more about ways it might actually provide public benefit.
Thank you. Tom?
Thank you. I'm a late addition to this panel. I think possibly it was geographic. Somebody needed to be from out in the West. It may also be related to the emergent nation of Cascadia.
Are you seceding?
We may. We're thinking.
I'm going to claim my Western Canadian citizenship at this point.
I represent a small consortium of scientists who are interested in marine cloud brightening. I could take some agreement and some issue with each of my three colleagues, but I'm going to focus my remarks a little differently because I'm going to focus on what would we do if we actually set out to do research. And I want to point out that in this slide, you see these bright streaks in the cloud deck off the west coast. Those are ship tracks. Those are evidence that if you add small particles to clouds, you make them brighter. So the real question for us in thinking about marine cloud brightening is, can we engineer this? Can we control that mechanism? At the onset of all this, I want to point out that this is a dual-purpose experiment, and I thank Joyce for identifying one of the real uncertainties in all of climate science, which is the aerosol-cloud interaction, which leads us to the problem of climate sensitivity and is one of the leading causes of changes in climate sensitivity and changes in what we see in climate models. So our experiment addresses that specifically in an experimental way. Okay. In one sense, our experiment is simple. That's fine. Yeah, in one sense, our experiment's simple. Put salt particles in a cloud and see what happens. It turns out, like with many things, it's a little more complicated. So I put up here on this slide the I can't even count this morning, 5 processes that need to be looked at. You need to generate particles. You need to look at how those particles disperse in the boundary layer, because what you're trying to do is inject particles in a source and have them entrained into a cloud. You then need to look at what happens to the microphysics of that cloud. By microphysics, we mean the number and size of the drops. If you introduce more nuclei, you end up with more cloud drops, all other things being equal. That's how you get brighter tracks. Then the clouds adjust dynamically to this change in the microphysics. The microphysics is not independent of what the subsequent evolution of the cloud is, or vice versa. So we need to understand that. And finally, we get down to the bottom, which is what we really wanted to know. How do all these changes actually end up affecting the albedo or reflectivity of these clouds? So our proposal is to go out and do this. And we have a project outline. The first part is to develop the sprayer. We actually have a nozzle that makes particles of the requisite size. They have to be less than 100 nanometers in diameter, which, if you're not into nanometers, means they're really tiny. We have to be able to generate something like 10 to the 14th or 10 to the 15th of those particles per second per square meter. So that's a whole lot of particles. It turns out the nozzle makes, about 100 less than we need. So we're talking about a couple hundred nozzles to form the sprayer. So the first stage is to build that sprayer. The second stage is to test that out along the coast and then out at sea. You say, why would you do it on the coast when you want to do it at sea? It's much cheaper to do things on the coast than it is out at sea. And finally, there's a limited field area experiment that we're talking about, which is roughly on the scale of 100 kilometers by 100 kilometers. So if you look at this progression, I want to inject some reality here into some of the discussions. Just to get this far in the diagram, given enough funding and continuity of funding, is a decade-long project at least. We're not talking about something that we can do in 6 months. Coupled in with all of this is the modeling side that Joyce has alluded to, because part of this is, can you actually predict what it is that you're doing in an experiment? So there's a real interplay here between the models, between the experiments, and that's always the way our field has worked. The one thing I want to point out is we are suggesting something different about atmospheric sciences. We're suggesting that we might become more like physicists than astronomers. We might actually start doing controlled experiments, which is what physicists have always done. The difference is we're doing them in the real atmosphere as opposed to isolating in the laboratory, because nobody knows how to make clouds. So let me end up by re-emphasizing 3 things. One, this is a dual-purpose experiment. It provides basic scientific understanding that is useful to the climate modeling community as a whole. It is limited in scope.
Oops. Sorry.
Sit, yeah. Oh.
It won't stop.
It is limited in scope. We're not talking about planetary effects here. We're talking about small-scale effects. And finally, it's environmentally benign. We're talking about spraying salt. We're talking about spraying salt over the ocean where there's already salt. And so I'll end with that. Thank you.
Sorry to keep barking. I couldn't get it to stop.
Yeah.
Well,
Sure, Doug.
Like is often the case
Sure.
with real dogs.
Sure, Doug.
Dan?
Thanks, Doug. So first of all, I just want to thank Lizzie and Gernot and David and Ted for organizing this. I know how much work it is to organize a meeting like this, and I've got to say it's also just amazing to see everybody here because I've been involved in these types of workshops and discussions for many years, and this kind of interest is very gratifying. It's great. I want to bring us back to the real climate world for just a quick second. This is a picture of the Arctic sea ice, like now. We're in the middle of an extraordinary event. Extraordinary event. And if you're a climate scientist, this is jaw-dropping. 2012, which you see in the green, was a pretty amazing year where you saw an incredible loss of Arctic sea ice. This is wintertime ice now. And the floor just dropped out. I mean, we're scratching our heads trying to understand what the hell is going on. Clearly, some of this is in response to the really big El Nino that we had, but even that doesn't explain this kind of change. As you see, this is just off the scale from previous wintertime sea ice coverage in the Arctic. Next slide. This is Antarctica, by the way. So didn't get a lot of press, but Antarctic sea ice, the bottom also dropped off the chart in terms of summer in the Antarctic and what's happening, just beyond any kind of previous record. I think there's something important that I think about that is important, I think, for everybody to understand. It's very likely that we've only experienced somewhere between 50% and maybe 2/3 of the warming that we are already committed to because of the long timescales in the climate system. This partly comes from the resolution of the paleoclimate measure of climate sensitivity and the short timescale measure of climate sensitivity. And it's something models do very poorly at. They're not trained on this, and it's not something you can get out of the models necessarily. There's a wide range of this. But what that means is that today we are already committed, very likely, to something like 1.5 to 2 degrees of warming. Okay? So this 2 degree, 1.5 degree, frankly, to me, it's a little ridiculous. We're already there. We're already committed to be there. It may take a century or 3 to get there, but we're already committed to doing that, even if we froze emissions, froze atmospheric levels at current levels right now. Another little fact that people should keep in mind, the warming over the land where we live is roughly double the global average. So if we're talking about committed to 1.5 to 2 degrees, it means we're committed to 3 to 4 degrees already over the land in which we live. Just to remember that. I was shocked by Rose's comments earlier in the social science panel, where she said that she has never seen a geoengineering scenario that was plausible to her. I would say the exact opposite. I would say that I have never seen a scenario with geoengineering that is preferable to one without.
The other way around.
Okay, sorry. The opposite, yes, you're right. Thank you, I apologize. Thank you very much.
Rose is smiling.
Okay, Rose is smiling. Let me be clear. I have never seen a scenario without geoengineering that's preferable to one with, in that I don't think people understand just what we're up against with climate. And that's what I want to inject in this conversation. This is not, oh my God, maybe climate will be worse than we thought, and therefore we have to use, we have to develop research on geoengineering as an option. The most likely scenarios for climate over longer timescales are devastating to future generations. Absolutely devastating. And by the way, sea level is an even more depressing issue. We're not going to have time to go there. It's bad. 1 minute. So this is a slide that just shows, and the print got small, but it's okay. It's 9 different questions that are required to get to a low. You have to answer all of these to get to a low carbon economy. Right now, we really can't answer any of them. Technologically, I would say that the probability of getting on a scenario that keeps CO2 in the atmosphere under 600 ppm, if I had to evaluate the likelihood, it's extremely low. I don't think we're going to be at 900 by the end of the century. I think we're going to be in the 600, 700 range. And we could talk about that. But it seems to me that we're hearing a lot from people, and especially in the social science panel, about what world we might want. And that's wonderful. I'm trying to describe the world as I see it. And I want to make this very clear. I'm not an advocate for geoengineering. However, as a scientist observing the world, this is not the world I want to see. It is the world that I believe exists. And the most likely scenario is not one where many countries come together and do some geoengineering effort to combat global warming. I suspect it's going to be lots of individual nations doing things in their own self-interest with some coordination. And the challenge for governance and for science is to work both on the coordination, but also the really difficult problem of attribution. Because if any country does this, they will get blamed for any weather event that happens regardless. And we have to be prepared to understand all of these different attribution issues, which are going to get very thorny and very complicated. I think it's a very difficult climate problem, and I think we're in the infancy of our understanding of this, and yet it is still, in every case that I've seen, better than the alternative of just letting the climate warm. It is not a substitute for emissions reduction. We still need to do that. But given the trajectory of the world and the difficulty of reducing emissions, this is something we really need to understand now. So I'll stop there.
Thank you. So I'd like to make sure that we have lots of time for audience questions, but we do have, well, I guess I have the prerogative from actually sitting up here. I wouldn't mind just a very, very brief ability for the other panelists to comment amongst themselves on what they've heard from their co-panelists. Starting with Alan and potentially commenting on your slides referred to what we could learn from modeling, what we could learn from volcanic analogs, but the potential for whether we need testing versus sort of waiting for the next large volcanic eruption. And I don't myself know what the status is of observing networks for the next, if a Pinatubo eruption occurred next year, would we learn what we need to learn?
All right, let me comment briefly on that and then ask a couple of the panelists one question, if you allow me. Yes, the Pinatubo eruption in 1991 was not very well observed. Our satellites couldn't see through the cloud. There were no LIDARs that looked up from below. There were no balloons that went up into the cloud in the tropics. And so a lot of what happened as the sulfur gas converted to particles, how fast it happened, was not observed. And so we have an opportunity to be ready for the next eruption. And I've worked on a panel with NASA, another one in Europe. Can we deploy balloons at all the different latitudes and test them every 3 months and then have a bunch of them ready to go up into the cloud when we have the next eruption, which we can't predict? Do we have the right things in space to measure these particles? And so I think we can learn a lot about geoengineering, but also learn a lot about volcanic eruptions if we're prepared. I just wanted to ask David and Dan a question each. David, I went up to Harvard a couple years ago to talk about this balloon project, and you said that you're only going to do it if it was funded by the federal government. And now I understand, because you haven't gotten funding, you're going to be doing it with private money. And I'm not saying that that's the wrong thing to do, but I'm just wondering, how do you address people that say this is a slippery slope in your own program? And Dan, I mentioned that there could be global conflict if people can't agree on what temperature we want. Don't you think that's a worse scenario than I know global warming also produces conflict, but can't you imagine that as a bad scenario for doing geoengineering too?
Great questions. Yeah, so we had said that we wanted to do the experiment. We'd only do it if it was dominantly publicly funded, and we're changing our mind. So just to be clear about that. So the funding that for this experiment, assuming we go forward as we're heading, is from internal Harvard funds that were basically the startup funds to me and Frank Kuich. That's not startup as a company. This is completely non-commercial, and we have a strong policy against commerciality and IP and for transparency. But it is internal funds of Harvard that were ultimately philanthropic funds. and as well as a larger effort that's philanthropically funded mostly from environmental philanthropies. And so we have changed our view, and in a funny way, in the current administration, I'm actually really happy about that. So I have real concerns about this administration's potential interest in this technology. I think if the Trump administration both slashes research for climate science and also cuts action on emissions, if in that same sense, which it's not a given that it will do, but it looks like it, it was also going to advance research on solar geoengineering, I think the best policy for researchers on geoengineering might actually be kind of active resistance, because and to actively stand up against the administration. Because my view is the long-term thing we need here is a broad and sustainable effort on research, which needs to have broad buy-in for many parties around the world, needs to be international, and I think if in that scenario that I suggested, the environmental advocacy groups of whom I'm in many ways a part would actively attack such a research program, arguing that it was just a distraction. So I think that wouldn't be a sustainable or sensible thing. So in that world, I'm actually much happier doing this experiment with funding from environmental philanthropies or sort of core Harvard funding than I would be doing it out of sort of new funds from the administration. But that still doesn't address the hard governance questions that actually are pretty independent of funding. And maybe we'll come back to those in a different question.
So I'll just say very briefly, Alan, that in terms of conflict, something I've been thinking about a lot recently. I have a postdoc working on conflict with climate change. And frankly, my judgment is that the likelihood of conflict from resource scarcity and migration driven by climate change impacts is far, far greater. Now, there is an issue about coordination and conflict related to control of a solar geoengineering system. I think it's absolutely certainly an important question to ask and an important question to look into. But if you look at the likely impacts of climate, sea level, impacts on food production systems, I just see it's incomparable in terms of the likelihood of conflict. And I think a lot of studies coming out of retired military folks would support that view as well. I want to just also briefly comment on the observing systems that you mentioned. To me, there's a fundamental problem with the volcanic experiment that is completely separate from the observing systems. And yes, our observing systems do not measure the full spectral radiation budget of the Earth very well at all. And it's a huge, important thing, not just for solar geoengineering, but for climate in general. And so the same systems we need for solar geoengineering are observing systems we need for the climate. And right now we don't have them. And therefore, if China started solar geoengineering tomorrow, we wouldn't have very good systems to understand what they were doing and what effects it was having. And that's a tragedy. We need to improve our observing systems. But the fundamental problem is that you can only do the experiment on the Earth once. So with Pinatubo, it was also in the middle of a big El Nino in '92, and frankly, you will never be able to figure out how much of that was the El Nino and of the cooling that was experienced post El Nino, and how much of it was Pinatubo. You will never figure that out because the variability is so much, and the Earth only has one. You've only done the experiment on the Earth once. That will be true in a solar geoengineering world as well. You do the experiment and you try to attribute, good luck, because you see an effect and you sort of say, well, do you believe the models or not? It's very tough.
You're absolutely right. I was just talking about observing the microphysics of the formation of the aerosol cloud immediately after the eruption, not attributing the impacts.
But attribution is a killer.
Yeah, absolutely.
Did you have a
Quick question for Joyce.
Yeah. So the question I have for Joyce is simply there appears to be a slight difference in the expected scale of experiments between David's balloon experiment and your suggestion of a tenth of a Pinatubo. And a related, so I was just wondering if you could comment on that.
The orders of
Can I make it?
And yeah, go ahead, David.
So, can I go?
Yeah, sure.
So like I said, picking a tenth of Pinatubo was sort of out of the air, but my fundamental belief is that you can try to understand the microphysics in a smaller cloud, and you can kind of tune your models to get the same result, but in the actual implementation of a broad injection of SO2, you would need a large enough injection that it was getting close to what you actually want to implement. And so that's kind of the slippery slope that requires some sort of governance in my view.
There actually might not be much difference between us. I think the key thing was in actual implementation. So at least the way I see it, there's a bunch of microphysical parameters in models. I mean, as you know better than me, you wrote some of the text. And we need to find ways to improve our knowledge of them. So for example, our experiment is all about that. And indeed, we're not just looking at sulfates. In fact, we really aren't looking at sulfates much. We've been thinking about other particles we might use that might reduce other risks. So for example, calcium carbonate in the stratosphere appears to reverse ozone loss because it reacts with some of the acids humanity put there, chlorine and nitric acid, and so pushes ozone back towards pre-industrial. So it also has other advantages of not heating the lower stratosphere. So there's some pretty significant advantages that we need
but might hurt cirrus clouds.
Correct. And so there's a bunch of ways that we need to test that carefully that are fundamentally microphysical experiments. So the way I see it is, first of all, to say the obvious. No one can test the large-scale way the climate responds to forcing except by doing it. And even if you do it, you don't know the answer. So we have put CO2 in the atmosphere, and we still don't know precisely the large-scale response to CO2 because of all the noise in the system. So once you start talking about implementation, there's no magic test that tells you climate response. But for microphysics, I think there's a way in which experiments want to be small. So I think, to summarize, my view is that the natural scale for experiments is that you actually want to do a whole bunch of really small ones, going at little microphysical aspects. And then, I think agreeing with you, if we ever get to a place where we actually, when again, who's we, where there was some group that was moving towards deployment, then I think it's true that you'd start with some subscale thing and monitor it.
But my point is actually that small experiment is not going to teach you the microphysics or give you the confirmation in your model treatment that you want if you want to eventually get to deployment. So this is the problem.
I think I'll just break in to say this is I think this is a very productive discussion to actually illuminate sort of where we are in terms of the natural sciences on geoengineering. That to a certain extent, this is an emerging field, and we haven't. I think I used to say several years ago, slightly facetiously, that we'd turn the sun down in climate models and notice that it got colder. We're clearly beyond that, but there's still quite a bit to know. So Tom, I've noticed you've been taking copious notes.
No, not copious.
Oh, okay. But I wanted to give you a chance to chime in as well.
I think part of the way I focused my remarks was trying to differentiate between research and deployment. And I think there's a tendency for us to start talking about research and leap to the endpoint of deployment. And if we don't separate that, we're going to get continuously confused about what we're actually talking about. And particularly in the kinds of things I'm interested in with clouds, we can do this at small scale. David can do microphysics at small scale. There is, and there are these other questions about what's going to happen when we deploy it and how would we govern it. But right now, we don't even know if it's possible. So I would really like to separate those two things and say there's a difference in talking about research and talking about deployment. I have a paper which we're in the second round of revision, hopefully will get published very soon, with Steve Gardner, who's an ethicist, looking at what the ethical considerations are for testing and how do you define tests versus deployment. So I'm not suggesting these are easy questions, but I think it's one that we need to keep in mind. I also want to follow up on Dan's comment about attribution, because this is something that in my own thinking and modeling on this I have run into. This is the wicked question, without a doubt. And I will just add, for those of you who don't pay attention, our climate observing system is not steady state. Our climate observing system is rapidly running downhill. In 5 years, it will be far worse than it is right now.
Absolutely. And only accelerated by the if the White House budget were to come to pass.
Yes.
So let's turn it over to audience questions. And as before, we'll take like 3 questions at a time. And if you can state your name and where you're from, that would help. Should be
Thanks.
microphones passing.
Thanks very much. My name is Alex Hanafi. I'm with the Environmental Defense Fund here in Washington, D.C. My question, I think, gets at one of the topics that Alan brought up in early on about the challenges for discussions around solar geoengineering, around where to set the thermostat, how you do that, and how you decide what that is. I'm curious as to whether you think and to what degree the Paris Agreement has helped in that discussion. In Paris, the countries of the world agreed that they would limit warming to no more than 2 degrees and pursue efforts to keep it below 1.5. So to me, that suggests there is at least some spectrum of agreement, somewhere probably between 0 and 1.5, or maybe 2. And so I'm curious about whether you think that has helped the discussion, and if so, in what ways? Does it help limit the range of disagreement and therefore make it a bit easier to resolve that question? Thanks.
Pass the microphone to.
I'm Rafe Pomerantz. This question is with my Arctic 21 hat on. I want to really support what Dan said.
Is that mic on?
No? There seems to be a diversity of opinion.
Hold it up.
Speak up.
Okay, I really support Dan. I think we have to move this debate in a different direction. It would really help move research, I think, which I support, strongly support. And that is to judge the need for this sort of research by looking at specific parts of the climate system that we have to have, or that we have lost already. Now, I want to use 3 examples very quickly. First is the Arctic, which Dan touched upon with the sea ice slide, but it's reinforced by snow cover loss, shrinkage of Greenland, permafrost thawing, and the loss of all the Arctic glaciers in Alaska and Canada, which are big contributors to sea level rise. Now, the real world question is, on May 11th, the 8 foreign ministers of the Arctic nations gather in Fairbanks. Okay, and 1 month before, 2 weeks before that, there's an IPCC assessment, a like assessment of the Arctic condition. So, what would you like to tell the foreign ministers? What is the Arctic we have to have, and how do we get there? And maybe SRM or the cloud brightening or cirrus steering are part of that package. So when you look at the specifics, otherwise you lose the big pieces of the global climate system, i.e. permafrost, carbon storage. I'll move along.
Yeah.
Second example.
I don't think we need
Come on.
multiple examples. We only have 15
The Great
minutes.
Barrier Reef, mostly dead now from coral bleaching. So climate, call it an ecological catastrophe, is behind us. Third, Dan hinted at, he was too depressed to talk about sea level rise. What do you do about the ice sheets? Can we contain the ice sheets under any scenario, including geoengineering? Because the ice sheet issue is upon us.
So I have, I see Mike and Oliver and Janos, and maybe we'll take all 3 of those and then turn it to the panel, just in the interests of time.
Okay, Mike McCracken from the Climate Institute, and I want to sort of follow on but generalize what Rafe said a little bit. Basically, the notion that's been discussed in the science community is that I'm going to do research until I fully understand it, and wait till I have full understanding. And I think we in the scientific community just know that's going to take a long time or forever. I mean, as David was saying, we don't understand CO2 fully enough right now, and so putting off what we do is just going to lead us to a worse and worse situation. So the other kind of approach is to basically start iteratively and learn. It's not one decision that one makes, except that you're going to try and learn iteratively. And I guess I would think the ethical analog would be what happened with AIDS medicine, where the the researchers were basically saying, well, we're going to hold it off and test and test and test. And the AIDS people came in and basically said, well, by then we'll be dead. And so let's move ahead and start doing some learning as we go. And I guess I'd like to hear the comment about, do we wait till we know everything, or do we try and work iteratively?
Hi, Oliver Morden. I was interested, a couple of you talked about this issue of attribution, and it struck a chord with me with what Rose was saying earlier about always treating problems as gaps. Should you not perhaps consider, I don't know who on the panel would like to take this, the idea that actually don't worry about attribution. Attribution is not a problem, it's a wicked problem that you're not going to solve. What you have to do is, if you can't have a governance system that's robust against contested attribution, then you've got a big problem.
Yep. Janos, one more, and then I'll pass it to the panel.
Janos Pastor for the Carnegie Council. I'd like to come back to the issue of experimentation versus deployment from a governance perspective, largely aimed at David, but maybe other members of the panel can also address it. So I get the concept of small-scale experiments that you're trying to do now, microphysics, chemistry, dynamics, etc. Yes, that's clear, and I could also envisage very nicely ad hoc governance mechanisms to make sure that those experiments are done correctly and there's buy-in and legitimacy and all that. The other end, I also get it that in order to really test the impacts on the climate system, you actually have to implement it. That's the only way we're going to find out, with or without attribution. Let's not get into that issue. But but for the governance of that will have to look very different than the governance of the small-scale experimentation that you're doing. So how can we break this down a little bit in stages? So that it doesn't become a simple slippery slope, but it becomes clearly identifiable stages, so that we can also develop governance for those respective stages. Thank you.
Thank you. So we have Alex's question, did Paris help in terms of where to set the thermostat? Rafe, what would you tell the foreign ministers at the Arctic Council? Mike on starting iteratively and learning. Oliver's question on attribution. And Janos's question about stages, doing the research in stages to avoid the slippery slope. I don't know whether anyone has
Oliver.
I want to start on Mike's question very quickly.
Okay.
So Mike, I think is exactly right that Mike McCracken said basically, this distinction that I think the way I think about it, Mike, is that the mandate for research right now, the urgent need for research, is not to perfectly understand it, because we never will. But it's, when I look at the future, I see a substantial likelihood that some country will try to do something in this domain. And therefore, I want to try to understand this as much as possible before they actually do it. I don't see it as a slippery slope to aiding them doing it. I think, if anything, and this is something that I think David and I both agree on, that a substantial fraction of the money that we're raising for the Harvard Solar Geoengineering Program, I don't know whether it's 20% or 30% or 50%, but a substantial fraction is going to go specifically to focus on all the ways that we could screw up, all of the ways that geoengineering might create problems. Because to me, you want to fund as much skepticism and as much research into the issues that you want to stay away from. I think we know, for example, right now, that if you were to do it today, you would not do it with sulfur. That would be a very bad mistake, even though a lot of the community still thinks of this as sulfur. But I don't think that's true based on what we know of the chemistry. But again, what we need to do is focus the research with the idea not that we won't decide whether this gets used or deployed. We will try to understand it so that whoever makes the decision, whatever country or group of countries makes a decision, that it can be done with a better degree of knowledge. There's still fundamental things we don't understand and we never will. The issue with land plants and hydrology and evapotranspiration is really complicated, and my suspicion is we'll never actually know exactly those parameters in the models, the soil moisture and everything else. It's amazingly complicated. Anyway, I'll pass it on to Tom.
Okay. I was going to follow up on Mike's question. and a little bit on this idea that if we don't understand everything, we can't do anything. We are doing an experiment right now that we don't understand. So let's not fool ourselves that we understand exactly what the climate system is going to do in the next 50 years. So we're saying, oh, we don't understand that. We want to do research, and I would go to the AIDS analogy. It's not a bad one in this case, because I would say that the doctors already had an idea of what would work and how to make it work, all right? And we have not got that same level of confidence in the ideas that we have, I think, as they had when they actually went towards. So I see this as an iterative process for sure. And I would say that we start with small experiments, and David's got a bunch of them, and I've got a bunch of them that lead on to bigger experiments, and we need to figure out how to do that. But I think we should disabuse ourselves of the idea that anything we do is going to make the world worse. We've already got a worsening world.
David, did you want to take one of the other questions?
A few, but quickly. Oliver, as often happens, said just what I wanted to say. The idea that we magically have to solve the attribution problem as a technical problem, I think, is just nuts. So there are thousands of people, U.S. citizens, dying today from Chinese air pollution. We don't know precisely how to attribute it, and we don't have a legal system to deal with it, and life goes on. The fact is, all sorts of things in international politics have spillover effects. We don't have perfect attribution. That's the world we live in, and the world is bumps along. So I think the idea that we need to magically know attribution is just a canard. I also want to pick up, maybe it's obvious, but Rafe said the exact, what we need is if there's a we and there's a fixed objective answer. I want to be clear that I think in terms of where to set the thermostat or what we need, these are inherently political questions. There's no objective answer about the right climate to aim for. I can tell you what I as a voter would vote for, partly because I like the high Arctic. I'd aim to bring us back towards pre-industrial. But that's not the right answer. It's just the answer I happen to vote for. And the idea that there's some kind of magic threshold at 2 degrees C or something else that we politically agree to, I don't buy. So from my point of view, these are deeply political questions, and they should be, because they involve values in a deep way, and that we need a better, more inclusive conversation about those values and answers. And with regard to Janos's question about how to actually move towards governance, I think that we don't have an answer, and the right answer for the next few years is to simply have more open conversations that bring in a range of different options for what governance could look like. And I think the biggest mistake we would make would be too quickly making a kind of implicit assumption that there's one way to do this.
Chris?
I think I wanted to address Dennis's questions about experiment versus deployment. And in my mind, that is where the most important questions regarding governance lie. In other words, I'm perfectly happy with Keith and Tom starting experiments at the level and size that they're thinking about, because I don't think that they're going to be disruptive in a way that is important to the whole conversation, for example, about whether or not and how much mitigation to start working on. But I think that there's a line somewhere between the size of Pinatubo and the current discussion of experiments that needs to be thought about and needs to have some framework in mind about when we cross that line. And that line is somewhere between deployment and experimentation. I don't know where it is, but I think that is the question for governance that needs to be addressed.
I'd like to address two of the questions. First of all, about the 2 degrees. That's not a global agreement that we will be happy with a 2-degree world. That's a pretty arbitrary level to shoot for so that people have something to shoot for in terms of mitigation. But as Dan showed, we're only at about 1 degree now, and the Arctic and Antarctic are already melting. Islands are going underwater, and so they would not be happy with 2 degrees. The 10th Arctic Shipping Conference, I think, is being held this week. So there are winners of global warming, and some people wouldn't mind it a few degrees warmer. So it's not a global agreement that we're ever going to get. People are thinking now about more regional geoengineering? Are there ways that we could control the climate in different places by different amounts? And there are computer simulations going on right now. Doug's doing some, and I'm doing some, and so it's not that we have to agree on one number. Maybe there's a scheme where we can look at more regional things by pulsing the emissions or brightening the ocean in certain places. So these are just early days, but there may be some ways that we could not just have to agree on one global number. But that's certainly, that's a pretty arbitrary number that's not an agreement.
Yeah, the big challenge is things for me like is something like, how do you protect Greenland, the ice sheet, but still allow Russia to have access to its northern ports that they're very happy with? That's a really hard problem.
Yeah. And the cover it with reflecting sheet. The other question is that the other assertion, which a few people made, is the only way we'll know how it works is by doing it. I don't agree with that. As we already discussed, we don't know how to do attribution. So even if we do it, how will we know whether the climate changed because of that or because of natural variability? And there's some things that are too dangerous to ever do. I mean, the government, I think, is now planning to spend $1 trillion over the next decade on modernizing our nuclear weapons arsenal without doing any testing, even underground. It's all going to be done theoretically in computers. And so if we could have a millionth of that money to do geoengineering research, we'd be really happy. So some things you can't just do outdoors because we only have one planet. And so we may just have to be happy with our climate model simulations. After all, why are we even worried about global warming? We have no observations of the future. It's based on the same climate models.
I want more than 1 million, but that's okay.
Oh, yeah. Well, you can have 1 millionth, and I'll take 1 millionth.
Okay, so I think, do we have time for another round of a few questions? We started late, because the first panel went late. We'll take 2 quick questions, but be quick, if there are still. So we have one up here.
I think Joseph might get in the Scannon Center. One of the most interesting things that you all sort of variously touched on was that the questions you ask or the type of science you're asking to do when you're doing research, geoengineering research, is a little bit different from what's been done in the past. Can you or anybody up there paint a picture of 10, 20 years into such a program, how our knowledge might be different from today in useful ways? For instance, understanding decade to decade trends in global temperature, or the effect of global temperature on general circulation, as 2 examples.
I think those are 2. Oh, I'm sorry.
Is there everybody wants lunch?
Well, let me just say, geoengineering research is intimately connected to climate research and the enterprise that's been going on for a long time with weather and climate. And so you can't just separate it. And things we learn in specific targeted research will be helpful for all of these problems. And so, and as we advance our understanding of climate variability, we'll know what things might change that on purpose. So you really can't separate them.
I disagree with that, actually. We have been doing, and I'll go back to what I said earlier. What we're talking about doing is changing, in some sense, the way in which we interact with the system. We have been passive observers of the system. We are talking about injecting things into the system and asking how the system responds, which is much more basic physics and chemistry approach to the world than astronomy or geophysical sciences. I think there are things that we can learn at this small scale for sure. This whole question that Joyce put up, all the questions that she had about marine cloud brightening, are basically, with one exception, on this small scale that would allow us to do that experiment, to compare the models, to develop an understanding we don't have now by doing it in a controlled space. So I think there are fundamental things that can shift our knowledge, and this whole interaction of clouds. Alan and I have had this discussion before about what you can learn from a model and what you can't learn from a model. I've cut my teeth on an experimental side of the field, and I'm pretty sure there are things I can never learn from a model.
But that's not what.
I think Alan agrees. I think
that's not what I said, Tom. That's not what I said. All I said is that what you want to do comes out of basic meteorology, and it's not coming out of left field. And and I'm not saying you shouldn't do your experiment. I think you should. I'm just saying that it's all that as things. I think I'm agreeing with you. What you learn will help us do better modeling.
I think maybe in between these 2 points, I mean, as Alan said, research on this topic is intimately tied to research on climate and atmospheric geosciences generally. And one of the things that means is because there has been so little direct attention to solar geoengineering, but it is building on this huge, more than a century of research in atmospheric geosciences, I think that there's actually a chance for surprisingly rapid progress. That is a serious research program in a decade, I think could really tell us a lot, because it's not starting from scratch. It's basically mostly connecting up a whole bunch of things that we half knew but haven't used for that application, plus doing some new focused experiments like the kind we're talking about. But even those experiments are building on the experimental techniques and knowledge that have been developed for decades.
And by the way, you can look back at the last, I mean, since 2007 when David and I hosted that workshop at the American Academy of Arts and Sciences, I would say there's a number of important things that we know now, including, for example, that you don't want to use sulfur. I would put that at the top of the list. That we didn't know then that we know now. And that's a big change in just 8 years. So projecting 10 years from now, I think we'll actually know a lot. Again, there will always be the potential for surprises. This is an Earth system that is unbelievably complicated. But lest you think that that's a reason to scare you away from going down this path, the potential for surprises in the real world without geoengineering, I would argue, is greater. I would say the magnitude of the experiment we're doing with carbon dioxide in the atmosphere is so massive that the potential for really terrifying surprises is even greater. But all the more reason for us to use as many smart people in the climate community as we can to think of all of the possible ways this could go wrong. All of the, I mean, to me, I personally am drawn to the asymmetries, ways that geoengineering doesn't work, doesn't compensate, because you want to probe those cracks. And that's what we need to do over the next decade, is probe as many of those cracks as possible and figure out just how devastating they are.
Thank you. On that note, thank you all. Thank all the panelists here. And where's lunch? Lunch is out there.